Welcome. This video gives an overview over the matching capabilities of Rust. They come in the form of the match expression, but there are lots more places where you can use matchings, and there's lots of different types of matchings. Let's see the guided tour. Let's first look at a few examples of matching. To this end, I have here an enum type with an empty enum variant, one with an integer and one with a string, and I derive debug. And I have a struct. The reason why I need all this is because the matching is very powerful and can destruct lots of types. So let's begin with command line arguments as we have seen before. The first example is a matching for literals. So here my value x, which is just the length of the arguments, is a value which depends on a literal. So here you can either pose a single literal, or you can put multiple separated by the or you can have a variable name which is a kind of catch-all and is then bound to the type which is in the match. So here I can then form various different variants depending on what literal I find. This here is again in a match statement. The next example is one we already know. You can match the variant of an enum and destructure it at the same time. So if, for example, if this is of type B here, then n is an integer, whereas s will be bound to a string. You can also destruct tuples. So here I have declared a tuple with an integer and a string, and if I match on it, I can put here a pattern which is a tuple, and so therefore I will be bound to a reference to an integer, and s will be bound to a reference of the string into the tuple. So I have destructured the tuple. I can also do this in a let command, which shows that let is actually another place where matching can take place. Here I have destructured the tuple into its two components. By the way, this is why I've used a reference here, such that the things are not moved in here, but are still available for further use. Note that here I actually move the components of the tuple out into these variables I and s. You can destruct arrays. So here I have an array of length 3 of 3 integers, and I can use this syntax, again a match syntax on the left hand side of an equals sign in a let, and take apart the array and give the individual entries their own name. Again, stuff is moved out here. You can also destruct structs. So here I form a struct as before, and if you put a struct destructuring matching on the left hand side here in the let, you can destructure the struct into its components. Let's see this run. Yeah, so if you study the program in more detail, you see that all this destructuring has actually worked. Now we have seen lots of different types of patterns. Now let's look at the different places where pattern matching can happen. I have my two types here, the enum and the struct again. First of all, in the arguments of a function, you can use not only names here, but you can also destructure the arguments as you go, like here. So function arguments are a place where patterns are allowed. This is what we had before. There is also if-let. That's an if statement where the if branch here is executed if and only if this pattern here matches. The same exists as a while statement, so you can let this loop here run as long as the pattern matches. For example, in this case here, I use a vector as a stack, and I pop from the stack until I get no more, which is indicated by the return type here being none and no longer sum of top. And in this let statement here, in the while let statement, I destructure as I go and combine it with a while. Same for for. Here you iterate over something, and you can destructure the values in the iterator just by using pattern matching syntax here. We have already seen that you can destructure and pattern match in let statements, and you can even do things like this here, where you interchange two variables by binding them anew with such a syntax. In function arguments here, I call the function above, and the struct I have here is destructured in the function argument as we have seen before. Name here is in the function then a string. Well, we don't actually, name is the name of the field, and this here means it's thrown away, and the variable a is now bound to the age value in the struct, actually to a reference to it. Let's run this. And if you study the code, you'll see that the matching has worked perfectly. There's one more important concept I want to explain at the same program here. There's two types of patterns. Some patterns are refutable and some are irrefutable. A pattern is refutable if it might fit or it might not fit. So for example, this pattern here for a struct, this is irrefutable, because whenever a struct of this type is given, then this pattern will match. But that's also necessary, because if the function is called with the right type, then, well, we have to execute it. On the other hand, the patterns here are refutable. In a match statement, it's allowed that the pattern does not apply. So for example, this literal here does not apply, well, if the literal value isn't a 2. So in a match statement, you can have refutable patterns, but usually in the end, you have to have an irrefutable pattern. For example, here, just the name of a variable is irrefutable because it matches to whatever it sees. So in most cases, you need as the last thing here, something irrefutable just to catch all cases, or you enumerate all cases. An if-let statement can have a refutable pattern, because if it doesn't fit, then the if-let is just not executed. Likewise, in a while statement, the loop can stop, so therefore the pattern here is allowed to be refutable. In for loops, the decision as to whether we move on or not is taken not by the pattern, so therefore this must be an irrefutable pattern which fits to everything that this iterator puts out. In let statements, the pattern has to be able to be applied. So either it has to be irrefutable, or it has to at least fit to the given type here, such that in this case it is irrefutable. And we have already talked about function types. Matching is an important concept in Rust. We have seen now lots of examples, lots of places, lots of different patterns, and it is very convenient to use, in particular with the algebraic data types of enums, but also with typical error handling and stuff. Very useful, very important, very exciting. Thanks for watching.